Hi everyone, my name is Diya Chivukula, and today I'm presenting my project, Computational Simulation for Aptamer-Based Detection of TDP43 protein as a Biomarker in Aphasia. This work focuses on how we can design a low-cost, stable, and computationally optimized aptamer to help detect early neurodegenerative changes connected to aphasia. To start, I want to ground this research in the clinical reality. Aphasia is a communication disorder that affects a person's ability to speak, understand, read, or write. It often comes from stroke, but in conditions like primary progressive aphasia, also known as PPA, the decline happens slowly and subtly. The problem is that identifying these changes is extremely hard. Current tools rely mostly on behavioral testing, which means that symptoms have to be noticeable before you get a diagnosis. There is no simple biological marker that clinicians can check early on, and that gap is exactly what motivated this project. A protein called TDP43 has become one of the most important indicators in neurodegenerative research. Under normal conditions, it helps regulate RNA processing, but when it misfolds or aggregates, it contributes to disorders like ALS, frontotemporal dementia, and certain types of aphasia. In primary progressive aphasia specifically, abnormal TDP43 deposits show up in the brain years before major symptoms. So, if we could detect even tiny amounts of TDP43 in accessible samples like saliva or blood, clinicians could potentially identify risk or disease progression much earlier. So, that brings me to aptamers. Aptamers are short, single-stranded DNA or RNA sequences that fold into shapes capable of binding to specific molecules. If you've heard of antibodies, they work similarly, but aptamers have advantages that can make them perfect for early-stage diagnostics. They're cheaper to produce, they're more stable, and they can be designed computationally with a lot of precision. For a target like TDP43, which has multiple domains and tends to misfold, having the ability to design and refine sequences digitally is a huge advantage, and that's why I chose an aptamer-based approach. So the main goal of my research was to design a computational aptamer that can bind to TDP43 with strong affinity. I wanted to model its secondary structure, test multiple sequences, and then run docking simulations to visualize exactly how the aptamer might interact with TDP43. Essentially, this project was about creating a strong computational foundation for a future diagnostic tool, something that could eventually be refined in wet lab settings. So here's the general workflow I followed. First, I generated several candidate aptamer sequences. Then, I ran secondary structure predictions to see how stable each sequence would be in a folded shape. Next, I selected the TDP43 protein structure that fits best with the aptamer binding. After that, I moved into the core of the project, docking simulations, where I tested how tightly each aptamer might bind to the protein. Finally, I analyzed the binding energy and interaction patterns to choose the best performing aptamer. So, for the design phase, I tested multiple sequences, each with slight variations that could affect stability or binding. Using structure prediction tools, I created folded models and checked their minimum free energy. Low energy usually meant a more stable aptamer, which matters because if the structure can't hold its shape, it won't bind accurately. After comparing secondary structures and energy values, I narrowed down the candidates to the top performing sequence with the best balance of stability and predicted binding behavior. Once I had my aptamer candidates ready, I moved to the protein model. TDP43 has several important domains, but the RNA recognition motifs, or RRMs, are especially relevant because they're known for interacting with nucleic acids. I selected a high-resolution structure of TDP43 and focused on these domains as the primary binding sites. Structurally, they offered a clear binding pocket and a surface that allows the aptamer to wrap or settle into place. The docking simulations were the most fascinating part. Using computational docking tools, I tested how each aptamer formed bonds with the protein. The best candidate showed a strong interaction with the RRM region and created multiple hydrogen bonds and electrostatic contacts. The binding energy was low, which is good, meaning the interaction is stable and thermodynamically favorable. When I visualized the docking pose, I could see the aptamer forming a snug, compact interaction inside the protein pocket. And interpreting these results helped me understand that not just if the aptamer binds, but why it binds well. Interpreting these results helped me understand not just if the aptamer binds, but why it binds so well. The structure fits into a region of TDP-43 that naturally welcome nucleic acids, and the aptamer's folded shape lets it anchor through hydrogen bonds, stacking interactions, and a bit of electrostatic complementarity. The stability seen in the energy minimization step suggests that the aptamer won't easily drift or break apart. All of this together tells me that this candidate has the real potential for detecting TDP-43 in a biological sample. If you haven't figured it out yet based on this graph, the 7th aptamer was the best aptamer since it had the most hydrogen bonds as well as the best fit overall in the protein. And even though the results were promising, there are definitely limitations. Everything was done in silico, which means it's idealized. Real TDP-43 in the body can clump, fold incorrectly, or even exist in mixed states that aren't captured in a simple model. I also didn't test how the aptamer behaves in fluids like blood or saliva. There are biochemical complexities that a computer can't fully simulate. And of course, to create a real diagnostic tool, wet lab testing and iterative SILEX cycles would be absolutely necessary. But even with those limitations, this project suggests that aptamer-based detection of TDP-43 is not only possible, but potentially powerful. In the future, I hope to refine the sequence further and eventually test it experimentally, ideally in collaboration with a lab that specializes in neurodegenerative biomarkers. If validated, this research could support earlier, more accessible ways to diagnose aphasia and related disorders, especially for communities that don't have access to advanced imaging. And with that, thank you for listening. I'm grateful for the chance to share this work.